Okay, this is homework set unit 8, lesson 3, day 3. This is question number 14, and this one deals with the Ferris wheel. So we get to apply cosine now to our Ferris wheel problems. And this one is saying that the center of the Ferris wheel at a county fair is 7 meters above the ground. So I wrote that here, 7 meters. And the Ferris wheel itself is 12 meters in diameter. So diameter is 12, which again means that the radius would be half of that. So radius is going to be 6 meters. That's helpful. And then the angular velocity of the wheel is 18 degrees per second. We're used to doing this in radians per second. This time our equation will be in degrees per second. That's going to affect our sinusoid, or in this case our cosine, by changing the angular velocity piece. So we got to be careful with 2 pi this time, involving 360 instead. But it's coming. Then we're supposed to write an equation involving the sine function that gives the distance y in meters above the ground of a seat on the wheel t seconds from the time that it is at the 3 o'clock position on the wheel. Well, let's get a little bit of a drawing going here. 3 o'clock position will be right there, so we know we're starting off there. No shift, because that's generally where we're supposed to start the sine function. But let's get this in our heads. How long is the radius? How high above the ground are we? So this is 6. We know that because it's half of the diameter, 12. And the height above the ground, well, 7 meters to the center, so this is 1 meter above. When we reach the highest point, then we would expect to see 6 plus 6, 12 plus the 1, 13 meters high. And we're also told that we can go 18 degrees per second. Well, that 18 degrees per second is going to be our angular velocity, all done up in terms of degrees. Not a problem. We can write that as a couple different ways. We might want to convert that to radians if we're used to seeing in radians, but I think we'll be okay too if we leave it in terms of degrees. Okay, so here's what we're going to do. Write an equation. Y is going to equal, well, remember we're dealing with A times the sine of BX, and usually there's an angle shift here, but there won't be an angle shift in this case, although I'll put it in here just to make sure that we take care of that idea. Plus the center line. Okay, so A was the amplitude, which is equivalent to the radius. So I know I start off with 6 sine, and then the B part is that's our angular velocity. Now it's okay to write this angular velocity in terms of degrees per second. Just make sure that our equation, if we have to graph it, is also in degree mode on our graphing calculator. So we'll let this 18 stay, and then we don't have a time shift, so I just have to put X in here. All right, or an angle shift because we're starting off at the 3 o'clock position, and then the plus C is plus the center line, so plus 7. So here's my equation that should give the full distance around. Now there's a hint here. It says hint, the seat will return to its starting point in 20 seconds. Another thing to think about then is if I wanted to rewrite this piece here in terms of time, I could write something like 6 sine of, I go 360 degrees every 20 seconds, X. Plus 7. One thing I want to check though, and hopefully you see it right away, is that 360 divided by 20, that piece, 36, if I take off the zeros, right, that'd be 36 divided by 2, which is 18. So this gives you the same idea, but note it's in 360 instead of 2 pi over 20, right? So this is in degrees per time versus radians per time. It still works the same way though. Just got to make sure when you graph it that you're in the right mode. So we're okay so far. There's our first equation. Part B says, using the equation you wrote in Part A, write an equation in T whose solutions are the times at which the seat is 10 meters above the ground, and then find all solutions between 0 and 30. Well, you'll note, though, that I used X, so maybe I should probably switch that over to a T to help the equation now. So I guess if you change these over to T's, you'll be in good shape. No problem. Okay, so we got part A. Let's take care of B now, and we're interested in we reach 10 meters above the ground. So we set y equal to 10, 6 sine of, I can use either one of these, but I'm going to use the 18, t, plus 7. So we'll solve this. I'll begin by subtracting 7. 10 minus 7 gives 3. 3 equals 6 sine of 18t. Next we'll divide by 6. Oh, there's a half again. That half coming out comes up an awful lot, and it references those special right triangles. Now note, in this case, we're in degrees. This is in 18 degrees. So when I do this, make sure that we're solving this in terms of degrees. So I'm going to reference my special right triangle here, and the right triangle is 1, 2, square root of 3, and the 1 is opposite the smallest angle, this time in degrees, 30 degrees, and this one's opposite 60 degrees. So that means that if I wrote this out, if I do the inverse sine of 1/2, that will be equal to 18t. Inverse sine of a half, 1 over 2, but I want 1 to be the opposite side of the angle. This is pointing at a 30-degree angle. So if I do inverse sine of a half, I should get out 30 degrees. Now, if you're in degree mode in your calculator, you can do the same thing by doing the inverse sine of a half. Now, I'm pretty sure we switched this over to degrees a moment ago. So if I do inverse sine of 1/2 or 0.5, sure enough, I get out 30 degrees. So there's my 30 degrees. That's equivalent to 18 degrees per second, if I'm concerned with the units, t. And if I divide by that 18 degrees per second, I'm going to get out time. And that time, 30 over 18, would be my value. Let's get that in terms of a fraction. That would be 5/3. Okay, so 5/3 of a second, okay, which is over 1. And if you wanted the approximation of this, you could easily get the approximation. We're looking at 1 2/3, or 1.67 seconds, to get to 10 meters above the ground. Okay, and that's how we solve question number 14.